All right, guys, we're going to get going with our angled check-in. So let's take a look at what they're asking us to do here. It says match each problem to its correct equation. Some answers may be used more than once or not at all. All right, so it's going to give us some options to choose from, but we're just going to go ahead and write down what those equations are without those options because we don't need those options. We know everything there is to know about angled forces. So the first one says a box of mass m is being pulled at an angle theta by a force Fp along a frictionless surface. The box accelerates to the right. Okay, so acceleration is telling us that the forces are unbalanced here. That's going to be important. It says, what is the magnitude of the normal force? Well, first thing we need to do is break up this force into its x and y components. We're going to see that right here. We have an upward force applied, or force Py, and then we have a rightward force Px. We also, if we're going to go ahead and just finish this off, note that we have force gravity acting down on this object, and then force normal acting up. If it's asking us to solve for force normal, we're going to have to use our net force in the y equation. So we know that net force in the y is equal to, well, let's go ahead and set our origin, saying that up is the positive y, and to the right is the positive x. So for this case, we would say that the forces that point up are positive, so that would be force normal, plus, well, force applied in the y is pointing up. Well, what is force applied in the y? Force applied in the y is the opposite side of this triangle. So force applied in the y can actually be found out using some trig really quick. We know that the opposite is sine, so that would be sine of theta is equal to Fpy over Fp. Multiply force over to the other side, and we find out that Fp sine theta is really just equal to force applied y. Therefore, we can finish off our net force equation up here and write that in, Fp sine theta. So after we add that over, then we're going to go ahead and subtract force gravity. So luckily, this object is just accelerating to the right. It's not accelerating up and down. So net force in the y is really just 0 because it's not experiencing any y acceleration. So we can say that 0 is equal to force normal plus Fp times sine theta minus force gravity. To solve for force normal, we're just going to add force gravity over and subtract Fp sine theta. Force gravity is really just mg, so we would get mg minus Fp times sine theta. And that's going to give us force normal. And this makes sense because our object's being pulled upward, meaning that force normal is going to be smaller than usual. Because force normal is usually on a flat surface just equal to mass times gravity. But since there's a force going upward on it, we don't need as much force normal as we normally would. So that's why we're going to subtract this applied upward force from it. Let's move on to number 2. Number 2 says a box of mass m is pulled at an angle theta by a force Fp along a frictionless surface. The box accelerates to the left now. What's the magnitude of the normal force? Well, all we're doing in this problem is just pulling it up to the left instead of pulling it up to the right. So we're going to notice that this force applied in the y direction is still pointed upwards. Since it's still pointed upwards and we still have gravity pointing down and force normal pointing up, and our object is still just accelerating in the left or right plane, it's going to mean that net force in the y is still just 0. Since that's 0, we're just going to end up with the exact same equation we did before, and that's because our force is being pulled upward. So force normal is still just equal to mg minus Fp times sine of theta. So again, the reason why we knew this is because if we were just to write that net force equation really quick, we would see that force normal is pointing up, and so is force applied in the y. We know that force applied in the y is just Fp times sine theta, and then force gravity points down. We just add and subtract like we did before, getting mg minus Fp sine theta equals Fn. How do I know that? Again, net force in the y is 0, so I can just add mg over and subtract Fp sine theta. I end up with the exact same answer as I did above, and that's because, again, this force is pulling upwards at an angle. Doesn't matter that's on the left side, it's still pulling up, and that's the important part. Next question says a box of mass m is pulled at an angle theta by a force Fp along a frictionless surface. The box travels to the right with a constant acceleration. What is the magnitude of the net force? So this one's asking us to figure out net force, so it's not that bad, but in order to do that, we're going to have to split up our applied force again. We notice that applied force in the y points up right here. We notice that applied force in the x is going to point to the right. We notice that we have force gravity pointing down, and then also we're going to have force normal pointing up because it's on a surface. There's no friction, so we don't have any leftward force. Since it's accelerating to the right, that's going to mean that we're experiencing an unbalanced force in the xward direction. And we know that for the x, given our coordinate system over here, to the right is positive. So Fp x is equal to mass times acceleration. We know that it's not accelerating in the y direction because it tells us in our problem that it's only accelerating to the right. So net force in the y is just 0. So we're really just concerned about this net force in the x direction. Well, Fpx is the adjacent side of this triangle. So what does that mean? That means that cosine of theta is equal to Fpx over Fp. It's going to tell us that Fpx is really just equal to Fp times cosine theta. Let's go ahead and substitute that into our equation above, and we end up with Fp times cosine theta is equal to net force in the x direction. Since there's only a net force in the x direction, that is our net force here, because the net force in the y is 0, so it doesn't matter for this problem. Letter D says a box of mass m is pulled at an angle theta by a force Fp. Same question as before. What is the mass of the box? Well, luckily, above we just solved for all of that. We found out that net force in the x direction is equal to Fp times cosine theta, but net force is also equal to mass times acceleration. So to figure out the mass, we just need to use this part of our equation. We divide by a, and we find out that mass is really just equal to Fp cosine theta over a. We have to use the x net force because the net force in the y direction is just 0. Since this is 0, we can't use this equation because we're going to find out that 0 equals mass times acceleration. Well, if we were to solve for mass, 0 divided by a is still just 0. And we can't have 0 mass, so that doesn't make sense. We have to use the net force in the x direction to solve for the mass of our object. Last question for upward angled forces. This says, what is the magnitude of the horizontal acceleration? Well, we know that it's accelerating to the right, so it's going to mean that we need net force in the x direction. We already solved for this. That's Fp times cosine theta. And we know that that's equal to mass times acceleration. Well, if we need acceleration, we need this part. All we're going to do now is divide by mass. So we get Fp times cosine theta, divide by mass, and there we go. We just solved for acceleration. Piece of cake. How do I know I have to use net force in the x direction? Keyword here, it says horizontal acceleration. All right, now that we're done looking at upward angled forces, let's start looking at some downward angled forces. This question says a box of mass m is pushed by a force Fp at an angle theta along a frictionless surface. The box accelerates to the right. What is the magnitude of the normal force? So let's go ahead and split this up just like we did before. We're going to notice now that Fpy is pointed downward and Fpx is still pointed to the right. So if we draw our free body diagram, we're going to notice that we have force gravity pointed down and then force normal pointed up. And then obviously these two components added onto it. So Fpy and Fpx. Technically, since Fpy and Fpx are components, they're not really on our free body diagram, so we would just draw the downward applied force right here. Because our free body diagram is to demonstrate the forces acting on the object, not the components of those forces. So once we have that, we can go ahead and solve just like we did above. Net force in the y direction is equal to the forces that point up, force normal, minus the forces that point down. Well, Fpy is pointed down, and so is Fg. What is Fpy? Well, let's go ahead and use our angle just like we did before. We're going to see that Fpy is the opposite side of that angle. So that's going to mean that sine of theta is equal to the opposite Fpy over the hypotenuse Fp. Multiply Fp over, we get Fp times sine of theta is equal to Fpy. This is the exact same thing that we got above, so nothing new has changed. So before we substitute that in, we need to realize that net force in the y direction is just 0 newtons. How do I know it's 0? Because it's accelerating to the right. It's not accelerating up or down, so since it has 0 acceleration in the y direction, the net force in the y is 0. So 0 is equal to force normal minus Fpy, which is Fp times sine of theta, minus force gravity, which is just mg. Add these two to the other side, and we find out that force normal is equal to mg plus Fp times sine theta. So we're going to notice here that when we apply a downward force, our force normal is going to be bigger than it usually is. Because on a flat surface, force normal is usually just equal to mass times gravity. But in this case, since we're applying a downward force, it's going to be mass times gravity plus this additional downward force. That would make sense because our surface not only has to support force gravity, but it also has to support this downward force, meaning that it's working harder than usual. Because it's working harder than usual, force normal is going to be bigger than it normally would on a flat surface. Next problem says a box of mass m is pushed by force Fp at an angle theta along a frictionless surface. The box accelerates to the left. What is the magnitude of the normal force? Hopefully some of you guys are realizing this is actually the exact same question as above. I just switched where the force was being applied to. So we know that net force in the y direction is just going to be 0, and that's because we're not experiencing any acceleration here. So since this is 0, that's going to tell us that 0 is equal to the forces that point up minus the forces that point down. So if we break this up again, we're going to see that Fpy points downward. And then we're also going to remember that force normal points up because it's pointing up from the surface, perpendicular, and force gravity points straight down. We're going to quickly see that we have the exact same equation we did above, which is force normal minus force applied in the y direction minus force gravity. We know what these two things are. We just solved for them above. So that's going to tell us that 0 equals force normal minus Fp times sine theta minus mg. Go ahead and add those two things over like we did above, and we find out that force normal is equal to mg plus Fp sine theta. And this makes sense because we're still pushing down on the object. Because we're pushing down on it, force normal has to be bigger than it usually is. And we talked about that above. Next question says a box of mass m is pushed at an angle theta. Same thing as before, the box accelerates to the right. What is the magnitude of the net force? So since it's accelerating to the right, that's telling me that the net force is acting in the x direction. We know that it's not acting in the y direction because it's not accelerating up or down. So the next step is to break up our Fp into the x and y component, just like we've been doing. So Fpy and then Fpx over here. Since we're only concerned about net force in the x direction, we only need the forces that point in that x direction. It says that we're on a frictionless surface, so the only force is actually Fpx. If we have our coordinate system, it's going to show us that to the right is positive and up is the positive y. Again, we only care about the horizontal force, so we're only going to care about this x direction. Why do I only care about that? Well, I only care about it because I know that net force in the y is just 0. If this is 0, it's irrelevant to my problem. Net force in the x, though, is going to be equal to the forces that point to the right, Fpx, minus the forces that point to the left. There are no leftward forces, so that's just 0, and that equals mass times acceleration. What is Fpx? Well, if I notice, Fpx is the adjacent side of this triangle. That means that cosine theta is equal to Fpx over Fp. Multiply over, and we find out that Fp times cosine theta equals Fpx. Substitute that into our equation, and that gives us a net force of Fp times cosine theta. So here's our next one, a box of mass m, same thing as before. What is the mass of this box? Well, we did this up above, and in order to find out the mass of the box, we need to use our net force equation, because we know that net force equals mass times acceleration. We just solved for net force, and we said that net force in the x direction is equal to Fp times cosine theta. So that is also equal to mass times acceleration. Well, if we need to figure out the mass, we need this part of the equation. In order to do that, we're just going to go ahead and rewrite it. Fp times cosine theta is equal to mass times acceleration. To solve for mass, you just divide by acceleration. Therefore, mass is equal to Fp times cosine theta, all over acceleration. Last problem, we made it. A box of mass m, just like before. What is the magnitude of the horizontal acceleration? So it's talking about horizontal acceleration here. So that's talking about net force in the x direction. Well, fortunately, we already solved for that. We know that net force in the x direction is just Fp times cosine theta. And we know that that's equal to mass times the horizontal acceleration, or acceleration in the x direction. So again, we're concerned with this part of the equation. Take it down here, Fp times cosine theta equals mass times acceleration in the x. To solve for acceleration in the x, we just divide by mass. We find out that acceleration is equal to Fp times cosine theta all over mass. So before we finish, I just want to talk about one or two things with these problems, and it's the similarities with the upward and downward forces. For downward forces, you're going to notice that it doesn't matter what direction we apply that downward force in, just so long as it's a downward force being applied. And what I mean by that is you can see right here between problem A and B that the force normal is the same in both of these cases. It didn't matter if I was pushing down on the right side or pushing down on the left. What mattered was the fact that I was pushing down on it. And if we look at an upward force here, we can see that for problem A and B for the upward force, when I pulled up on the object, the force normal was the same, regardless if I pulled up on the right side or pulled up on the left side. I found out that force normal was still equal to force gravity minus the y component of the pulling force. And again, if I pulled up on the other side, it was also equal to force gravity minus the y component of the pulling force. We talked about this before and the reason why it makes sense, and it's just plain and simple that if we're pulling up on an object, we're relieving some of that force that the surface needs to support. So when we push down on the object, we're actually adding more force to that surface. So the surface needs to support more of that weight. And since the surface needs to support more force, we're going to end up making force normal bigger when we push down on that object. So again, just summarizing, pushing down means that you're going to have a bigger force normal. Pulling up means that you're going to have a smaller force normal. And that makes sense because when you pull up on things, you technically make them lighter. And when you push down on things, you make them heavier. A way to envision this is pretend that you're laying on the ground and then your little brother jumps on top of you. If your little brother jumps on top of you and you try to get up, it's going to be a lot harder to get up now. The reason it's a lot harder to get up now is because there's more force pushing you down. But on the flip side, let's say that you're on the ground and you're trying to get up and you ask your friend to just grab your hand and pull you up. Well, it's going to be a lot easier for you to get up now because you have less force pulling you down. Since your friend is pulling up on you, they're actually helping you out, which means that it's going to be easier for you to get up. Not a perfect example, but good enough.